Example I want to take a look at comes from your textbook. It's on page 109, and it says this. A woman whose mass is 80 kilograms is standing on a scale in an elevator that has an initial upward velocity of 3 meters per second. The woman then accelerates upward at 2 meters per second squared. What is the apparent weight of the woman as indicated by the scale? Let's start with a free body diagram. The weight is easy. She has a mass of 80 kilograms. The earth is pulling her downward. Whether she's accelerating or not, the earth pulls her with a force of 800 newtons. That force is not going to change as long as she remains relatively close to the earth's surface. Here's a caveat. In future lessons, we're going to let the person actually get far from the earth's surface, and then the weight might change some because the acceleration due to gravity, 10 meters per second squared, may change as a result of that, and we'll figure out how to handle that in coming lessons. Now here's the normal force, and we're asked about what the apparent weight of the woman is, so we're basically trying to figure out what the normal force is. Okay, now here's an important point. We have to choose a direction to be our positive direction. It could be up, it could be down, but we have to make a choice. And when that happens, then that's going to determine how the signs, S-I-G-N-S, of the vectors appear in Newton's second law. This person is accelerating upward. I'm going to choose that as the positive direction. We're told the acceleration is upward at 2 meters per second squared. And so I'm going to indicate that in my diagram as well. Since up is my positive direction and my acceleration is upward, then I'm going to write the number for the acceleration as a positive number when I get to Newton's second law. So let's apply Newton's second law to this particular situation. So there's the equation, and now I'm going to write what the things are in the equation according to the variables that I have listed in the free body diagram. In other words, the net force is the upward force, or force as if there were more than one, minus the downward force, or forces. The normal force minus the weight is the net force in this case. And I made the normal force positive because I called up positive in my coordinate system, and I made the weight negative because I called the weight, the downward direction, negative. Now, I'm trying to find a number for Fn. I could feed in my numbers at this point, use TI-solve, and that's going to solve the problem for me. Or I could algebraically multiply both sides by the mass, then add the weight to both sides, and I'm going to get an expression for the normal force. I'm going to choose to solve it algebraically. Now I have an expression that I can put numbers into. So there are the numbers, and my calculator will give me some result. The reading on the scale is 960 newtons. And that makes sense because as I accelerate upward, I expect that I will feel heavier. My legs feel the normal force, or the pushing of the floor or the scale of the elevator against me. And so I feel heavier when I'm accelerating upward. Now, notice something. The initial velocity is a number that doesn't even appear in this problem. It may appear in some other problems, but velocity is not the same thing as acceleration. So the fact that the elevator was moving already doesn't even enter this problem. The force depends only on the acceleration. It doesn't depend on the initial way the elevator is or isn't moving. Okay? So let's try something with an acceleration that's in the opposite direction. So let's go to another example. Example 15.5, which in your textbook is on page 111. The initial downward velocity of a 56 kilogram woman is 1460 meters per second. She then accelerated downward at 3 meters per second squared. What is her apparent weight? Now, your authors have chosen an initial velocity that is unrealistic. 1460 meters per second. That's 1.46 kilometers per second. That's nearly 1 mile per second that this person is traveling downward. So she's then going to accelerate downward. Okay, I'm sorry, this is an unrealistic initial velocity, but that's the one that our authors give us. So let's just go with it. The same thing is likely to be true in problems that you get in your textbook. There'll be some unrealistic things that are posed to you. I would like to think the AP exam will be better than that, but I don't know. We'll see when you actually get it. Let's begin with the free body diagram showing the forces and the acceleration. Now I'm going to work this problem twice. In the first way, I'm going to choose a coordinate system that's in one direction. The second way I work it, I'm going to choose the coordinate system in the opposite direction. In either case, the only thing that's going to change is going to be the direction that I call the positive direction. So let's begin with up positive like we did in the last problem. All right, if up is positive, I'm going to work this all in the same color, then I can write Newton's second law and solve the problem. Now when I feed in numbers, I need to be careful because the acceleration being downward is opposite the direction that's positive. So when I put a number in for the acceleration, I'm going to have to put negative 3 meters per second squared in. There's the equation solved for the normal force. There are the numbers fed in. Notice the negative sign with the acceleration. And there's the numerical answer, 392 newtons. Let's do the problem again, but this time instead of up being positive, let's call down positive. All right, so now I can write Newton's second law, but this time since down is positive, the force that's in the positive direction is the weight, and the normal force is going to be negative as a result of that. Since the acceleration is in the same direction as the positive direction, then when I put the number in for the acceleration, then I'm going to put a positive 3 in this case. There are a couple of steps of algebra in which I've solved for the normal force. Now I'll feed in the numbers. Now notice I've put a positive number in for acceleration because the acceleration is in the same direction as the positive direction in this part, the way that I'm solving it here. And I get the same answer, 392 newtons.